Very good morning to everyone. Today we are going to discuss about bootloader design. What is bootloader? Bootloader is a small program which is placed inside a microcontroller to transfer the code from from external world. That means from the PC you can transfer the X file to be flashed to the microcontroller, and then you can renew your software right now. So you cannot do that just like that, because when you want to change the microcontroller program flashed inside the memory of controller, you need a flasher, and then you have to connect your chip to that flasher. There should be a software interface as well to transfer your X file to that microcontroller right now. So this is how flashing used to be done. So there will be a separate hardware for flashing, and you have to connect microcontroller to that flasher. Then there will be a software interface as well. Using that, you will transfer your hex file, that means executable file, to the microcontroller. Now I am doing it like that only. Till now, whatever, I think we did some 2 sessions, right? In these 2 sessions, we have used only that flasher to flash the software. But this is very tedious, because every time I have to remove the controller from the motherboard and have to connect it to the flasher, and then I have to load the executable in the software interface and how to transfer it to the controller for flashing. And this sometimes, if this is a simple motherboard, no issues. Sometimes the microcontroller will be fixed in the motherboard. Microcontroller fixed in the motherboard, right? That will be of SMD type. Now I am have a DIP type microcontroller. Those SMD relate microcontroller, when you remove it from the motherboard, you will broke the controller, so that the entire microcontroller will become faulty, and you cannot reuse it. Even you cannot reflash that one. So these are the practical challenges that we have when we work with a microcontroller to develop some product. All embedded product will have this challenge. The same challenge is applicable to automotive industry as well. When automotive ECU, when you want to flash the automotive ECU, and which is fixed in a vehicle, it is very tedious, like removing the microcontroller from the ECU, removing the ECU from the vehicle. By doing these actions, you will spoil the ECU as well as the controller. That's why they developed a mechanism. They developed a method. So using that method, it's just a program. Actually, that method is nothing but bootloader. This bootloader is a small program, a straightforward program, which will receive executable from outside the world using a communication bus system. Maybe it can be, the communication bus system can be a CAN, your RS-232, or an USB, I2C, SPI, whatever it is. You can receive executable to be flashed via a communication channel. Upon receiving it, you will have a program which can work with the program memory. That means for a flashing, you have to access the flash memory, right? For that, there will be you have to write a program. That program will take care of receiving executable from the external world and flashing that to the microcontroller. In this way, the people can renew the software. Every day in our everyday life, every one of us using bootloader in one or another way. Most of you are having a laptop. The bootloader helps us to load OS from the hard disk of the computer to the main memory. So there is also a bootloader. Every laptop used to have a bootloader. You have a mobile right now, Android mobile you have. So sometime when a new version of Android version is when new version of Android is released, you will get a notification in your mobile that do you want to renew the OS, right? No. So when you say yes, the bootloader will be activated. Maybe it is like in different ways. Maybe it may have, they have a different name, over the air method or technology. Using that, it will communicate server which is having Android OS. From there, it will get all the executable via telephonic channel. Then it will flash that in your mobile. So in everyday life, without knowing, we are using bootloader in one or another way right now. So the same thing we are going to do it for our ECU. That is ECU that we are going to develop from a hardware software. No, so that software also need, that ECU also need bootloader, because many times when we will change the code, we will fix something. In that time, when we have to change the software, we cannot use the flasher every time and then remove the microcontroller from the motherboard. These are this is time consuming, right? For that, we are going to have our own bootloader. To prepare this bootloader, I spent nearly more than 10 to 12 days, because it is a little bit a tricky concept, and I have studied some sample codes available from Microchip for bootloading. After going through all those things, I decided to go for our own design, like whatever that we have in the code, that is assembly code provided. It's a little bit hard to understand, but it has a lot of clues in it. I used those clues, and I created a C version, embedded C version of bootloader, which can do that task. So developing the bootloader alone is not enough. From the PC side, you should transfer the X file to be flashed to the microcontroller, no, right? For that also, we developed our own application. I believe this is a very, we are in a very beginning stage. We want to make this application to the very advanced level, to analyze the traffic of every bus system, like CAN, LIN, MOST, everything. We want to create our own bus system analysis too, right now. To do that, in the very first time, in the very beginning, we want to initially work with serial communication interface, which is nothing but RS-232. Right now, why I am speaking about RS-232 here, the bus system that we are going to use to transfer the X file from the PC to microcontroller is RS-232 bus, or serial communication interface bus, that we are going to use it. So using that, we are going to transfer our executable code to the microcontroller right now. So now we have two parts. One is PC side, we need an application which accept the X files and then transmit them to the microcontroller right now, to the microcontroller. And the microcontroller side, we need a code. That code should monitor RS-232 port of motherboard and have to get the instructions from the PC. Then you should use that information to flash the executable. That is what the thing right now. So I am not going to detail. There are other serial communication, the software which uses serial communication for flashing right now. Those are available in the market. So I'm not going to explain that part of the code, but I am going to explain how the flashing works. Bootloader side, that means how the flashing works from the microcontroller side. That is I am going to explain in this session. Let's go to the session now. This is just like an introduction that I gave you. So moving forward, So initially, what is bootloader? So these are like theoretical information that I gathered from internet. A bootloader, also spelled as bootloader or called bootstrap loader, is a computer program that is responsible for booting a computer. So the every laptops used to have a bootloader. So right now to booting OS from the hard disk. With respect to embedded controller, a bootloader is a small piece of code that resides at the beginning of the program memory in the microcontroller. So I believe it is not like the term used here, no, beginning of the program memory. So I have the bootloader that we are going to design now. We have kept the bootloader at the bottom of program memory. So it's not like always you have to keep the bootloader at the top. You can keep the bootloader at the bottom of the my program memory as well. So actually this term is no, I'm not agreeing with that term. It's not like bootloader needs to be always at the top. You can keep that at the program memory, but when it comes to computer booting, in that case it can appear at the top. So you have your independent. So you can keep the bootloader at the top of your program memory or at the very bottom of the program memory. So whatever is very suitable that you can do. For me, keeping the bootloader at the bottom is, I feel it is very good because I can always start my uh, user program with the address 0. If you start the bootloader at the beginning, I will occupy some 200 memory location or something like that. Always I have to start my microcontroller program with the offset of 200. That's not, I don't like it. That's why I pushed my bootloader at the bottom of the program memory right now. So what they are doing, what our bootloader going to do? It enables the UART communication and allows the user to program pick with a serial cable rather than using a dedicated programmer every time you want to update the code. So now we are not going to use a flasher. Instead, we are going to flash the bootloader only one time, and then we can reflash the software using that bootloader n number of time. Right now, that is the technique that we are going to use. The people in the automotive industry, they use something called as UDS spec, diagnostic spec, right now. So I believe we have explained in our traditional sessions about diagnostics. In that, we have told like the diagnostic can be used for flashing the software right now. So the diagnostic layer itself act like a bootloader in automotive ECUs. So because using diagnostic, you can flash the software. You can transfer the code from the external world to your microcontroller. Only thing is your diagnostic should be flashed at the beginning. So that is the first software that should be available in the microcontroller before you flash your user program, user application. Right now, that is a different. So we are going to target, we are going to convert our bootloader to meet the UDS spec. Whether we are going to try that, or whatever that the UDS spec right now. The UDS spec is not for only CAN. You can apply the concept of UDS in every bus system, whatever the bus system, but there should be a communication bus system. That is the next level of development that we are going to do. Before doing it, we are going to try a simple, straightforward, easy bootloader, which can flash the software by receiving executable from the PC. That is what our aim now. So for that, I have drawn a interface diagram. So you should have an user application in the PC right now. So in our case, our user application will be called as Jassasa. That is, Jassasa is an Arabic word. The meaning of that one is spy. So we are going to spy the bus system network, and then we gather the information from there and we are going to populate them in our homegrown application right now. So right, so this application going to act like a host application in the PC. The Jassasa that we are developing right now, that is going to act like a host application from the PC side. Then the communication bus system that we are going to use is an UART. that will communicate with the motherboard of the microcontroller that we have now. Right now, in that motherboard, we have we have a microcontroller, right? So in that microcontroller, we are going to we will flash the bootloader using our traditional method. Using a flash, I will flash the bootloader first. After flashing the bootloader, I will activate the bootloader. Once the bootloader is activated, we are going to use this PC based application to communicate with the bootloader via UART communication, and will transfer the executable to microcontroller for flashing. That is what we are going to do right now. So in this, in our product, we are going to have the bootloader at the bottom of program memory. That is the thing. So the key modules that we have to develop to achieve this one, in order to develop a bootloader, these are the things that we have to develop. A host program which can decode an X file and transfer the code via UART to microcontroller. In our case, it is our application Jasasa. Then a microcontroller program with UART implementation, EEPROM flash programming. So we need a program. We have developed a program that is in a very earlier stage. We will upgrade that program day by day to meet the industrial standard. But we have our own implementation that is working. So we have a working model right now that is developed via C programming. Then the hardware UART circuitry, that means serial cables, and then motherboards, the motherboard to connect our microcontroller, all those things. These are the modules that we need in order to achieve this mission right now. Also, when you want to when I say I transfer a file from PC to microcontroller right now, how I am going to do that? When I create a program in MPLAB IDE, upon compilation, I will get an X file. That file is an executable file. Right now, I have to transfer that file content only to the microcontroller for flashing. That means to the bootloader for flashing. Only then the flashing will happen. If that is the case, I should know the file format of this one, like X file format. I should know about the X file format right now. So this is like this I gathered information from the website, Microchip's website, about their X file format right now. So they are divided their X files into different fields, and they have an explanation for everything. Field 1, start code 1 character. This character is an ASCII colon. So the colon has been used as a beginning of your record right now. For that, they use it. After that, byte field 2, the byte count, 2 hexadecimal digits. That means 2 digits. After semicolon, sorry, after colon, you have 2 digits for byte count. That means how many bytes you are going to transfer in that from that record. So totally that record is having, in this example, 6 programming word right now, program data. So that will be encoded after colon right now. So these 2 digits indicates number of bytes x digits pair in the data field. Maximum byte count is 255. That means FF. For example, 16 means you will have a 10x, 32 means 20x right now. So these are the common way, representation used to show that the byte count right now. Usually it will be multiples of 2. Then field 3, address. The address field is 4 digits right now. So here we have that means 4 digits address right now. So these four digits represent the 16-bit beginning memory address offset of the data. From there only, that means in the program memory where I have to flash these program data. I have told, right, 6 program data we have. From which address I have to flash? So here the address is 000. That means from the beginning of the address we are going to flash. Right now, the physical address of the data is computed by adding the offset to previously established base address. Right now, so the physical address means once see I told right now 0. 00 is a starting address, but I have 6 words. Right, all these 6 words. I think this is one word. Sorry, this is one word. This is one word. Another, actually, totally 14 bits programming words we have. Right now, 3 we have. Right. That means 2 bytes. Otherwise, 14 bits will become a one word. So like that, we have 3 word. Right. 3 into 2, that is 6. So, okay, I can say that I can flash 0, A12 at the address 0, 0. Then where I have to place 8A flash 8A11. So that should be the next address. So that they are computing by adding an offset, because that is going to be the next address. So that in address 1, they will flash it, and address 2, they may flash this OC and 28. So like that it used to go. This provide a memory addressing beyond the 64 kilobytes limit of 16-bit address. The base address, which default to 0, can be changed by various type of records. Base address and address offsets are always expressed as a big endian value. So it is like the numbers that we represented in these X files are in big endian nature. So actually your MSB is 12 and LSB is A. Right now, actually, in order to find out the actual value, actual programming word, you have to reverse. 12.0A is an actual programming word. So they keep the LSB first and then MSB in the second position. So you can add the offset to the base address to find out the physical location of every programming word. That is what that they are trying to say here. Base address, which default to 0, can be changed by various type of record. Base addresses and address offsets are always expressed in big endian value. That big endian, no. So in big endian, the LSB will be first and you will have an MSB. Right. The fourth field is record type. The record type, again, a 2 hexadecimal digit. Right now, it can have different value from 0 to 5. Each value has their own meaning. Right, 0 means data, 1 means end of file, and 4 means extended linear address. Mostly we use data and then end of file. These record types will be fine. We can find these record types in our expert most of the cases. Right. So here is an example for that. 06 is the size, and then address 0000 is an address, and 00 means it is a data, program data. So that's why they have 00 here, right? Then the program data that should be flashed, right? That is field file, a sequence of n bytes of data. Data is represented by that is 2n hexadecimal digits. Some records omit this field. The meaning and interpretation of the data bytes depends on the application. Right, then at the end, the sixth field is checksum. The checksum is computed from your beginning. That means from the size of first field 1 to field 5. Using all those fields data, the checksum is computed. The checksum is 2 hexadecimal digits. These 2 digits represent a computed value that is used to verify record as no errors by ensuring the summation of each of the bytes in the line adds up to 0. C, the calculation of checksum section. See, this is the record that we assume that is the record that we have in our X file. So this is example record from X file. We have to compute we have to compute checksum for this. See, actually, the X file itself, you will have the checksum at the very last. See, 0f is checksum for this record right now. When you transfer these data to microcontroller, you have to compute the checksum using the data that you received from the size till the last byte of the data that you are receiving, programming data right now. You on using all this field, you have to compute your checksum. Checksum is nothing but just an addition of the bytes, right? So what they are doing, so data bytes we have, see, this is the address and record type is data, and data bytes are these. The checksum in record checksum that we find in the record is f. Then the same you have to find the checksum in microcontroller side as well, right? Before you receive the checksum byte from the PC, you will be ready because you have from the size to last byte of data is available with you. You can simply add them to find out the sum of all records. Then to calculate the checksum, there is very easiest formula. Just subtract your checksum, that is the checksum value that you computed in the microcontroller side from the 100x, right? Sometime your summation may be more than 1 byte. That means it can go, for example, 2f1, 2b, 231, 2b2, something like that. It can have more digits now. Always you can take 2 bytes. That means, oh, sorry, 2 digits, only 2 nibbles. Least 2 nibbles from that checksum, from that summation right now. So if you just take that and you subtract it from the 100x, you can get your checksum value. So from my view, very easiest way to compute the checksum in microcontroller side is like simply declare an unsigned character variable, because its maximum limit itself 255 only. After 255, it will roll over right now. So when you add a value, when you add the byte values from the size to last byte of your data, if your sum exceeds more than 1 byte, automatically there will be a rollover. Right now it is limited coming back to that is 1 byte data. Then you can subtract that 1 byte data from the 100x to find out the checksum. This is the very easiest way to find out the checksum in microcontroller side. This is the thing. Now we know X file format, and we know what we have in the X file records, but we have to write microcontroller program for bootloader now. Right now, for that, here is the program that I have. So I call that program as bootloader. Right now, this is the source file. So in this source file, I have the pragma definition. This is that we used to do in every program. And then I define some of the parameters. These information I have taken it from that the sample code or a bootloader code provided in assembly by the microchip. I converted that into embedded C. That's all, nothing more than that. Here we define our external frequency. That means external clock frequency as 20 megahertz, because my board has that one. And then the board that we are using is 9600, but here I define 19,200. Actually, why I switched from 9,600 to 19,000, from 19,200 to 9,600. Reason behind that is, in my motherboard works well, and in 9,600, when I try to transfer the data with the baud rate of 19,200, I got some sort of errors. Maybe that is due to my cables, or I don't know the reason behind that is. As there is an error in that, I simply change that to 9,600. Everything worked fine. So I want to use that one only. So here there are certain definitions. So these are different commands that we can send it from PC side to microcontroller. When I want to write, I will use E3. When I want to bring the attention of microcontroller, that means to switch to bootloader or something like that. In that time, I can use EA. And when there is a when my data that is received from the PC is okay, I can use data okay, status byte E7. And then if data is not received properly and there is an error in the data, there is a checksum mismatch. In that time, I will put data bad things. If I am unable to write a data, I will say write bad. If I am successful in writing, I will say write okay. Like that, we have different commands here. Then we have a declaration of variables. Right, we have a functions send byte, put byte. Send byte will transmit the data from microcontroller to the PC. Right. The put byte is a subfunction of this, but both of them are doing the same job. Write EEPROM will write that is received data, program data to the flash memory. Right now, the get byte, this function will send byte will transfer from PC side. Get byte will receive from microcontroller side. See here, when that receive interrupt flag is not zero, that means there is a valid value that we have. In that time, we will simply take the content of RC register, which is nothing but we have a valid received data in that one. And then we have a inst ident function. This will transmit, it will transmit from the microcontroller side. This will transmit IDAC right now. So it will transmit from microcontroller to the PC. Here is a foot byte function. When there is a character to be transmitted, they will check whether that transmit inter flag is not busy. And in that time, we will transmit that character using TX register. So let me go back to main function so that you will understand properly. This is my bootloader program. Right here, this one I configure my baud rate to here it is baud rate. I have just activate my SCI module, and then I configure TX and RX pins. Then I select the high baud rate. I enable transmission. I set the baud rate. Then I wait in an infinite loop. After doing it, I also enable timer 1 interrupt. Sorry, I set the interrupt flag to 1. Here we have an infinite loop. Here what it does, it get the byte from the PC, it receives, and then you store that in the data, right? When I receive a data, I also transmit the data back to the PC, right? So if the received data is E3, which means a write command, then it calls inst write function. Inst, that means instruction underscore write function. So when that is called, right, we initialize the check one, that means the checksum variable to 0. Then we get the byte from the PC. That means the PC is transmitting the byte, we are getting it, and we give that to count, a variable called count, and that count is assigned to amount. Then we add the received count, that means received byte to check one. After that, next 2 bytes, as per the explanation that we saw in X file format, after size, we have address. That means higher MSB address, LSB address. So the received addresses are stored in the MSB as well as LSB. Then they are also added to checksum variable. So in order to find out the checksum from microcontroller side. Then the record time, even the record type is added to checksum. Then what we are doing, if the address, the MSB of address is not equal to 21, that means it is EEPROM data. If it is not EEPROM data, and then it is coming to receive data. Then it calls the receive underscore data function. This function, what it is going to do, let us check. The receive underscore data is another function that we have. This is the receive underscore data. This function will simply receive the bytes from the PC and will store them in a buffer because those are actually program data bytes. So whatever that we are getting, we are storing that in a buffer. Also, we are adding them to checksum variable so that the checksum is computed. When the last byte of the data is received, they will exit this loop. Then whatever the value that we have in the checksum, that we are subtracting from the X in order to find out the 2's complement. That is the aim. That is the checksum that we have to compute, right? Then after computing the checksum, I just transmit my computed checksum to the PC, right? Also, I get byte. That means after the last byte of data that I receive from the PC, the next byte will be checksum from the PC side. That means the checksum from the transmitter side. So the checksum computed by the receiver should match the checksum transmitted by the transmitter. If both are equal, the data is valid. If it is not equal, there is a issue in the communication. So we don't have proper data in our hand. So if they are not equal, we send a status byte called data bad. That means there is an error in the data. Maybe we can retry for transmission. So those things we have to implement. I will do that in upcoming sessions. If it is okay, if the receive data is okay, we send the status flag data okay. Then we go to a function. Then we call a function write underscore EEPROM. This function only going to flash the byte in, that is the received record, to the memory. So this function initially receive, it is getting the inputs from the MSB address and LSB address, right? And then if the address is not equivalent to EEPROM address, then what we are doing, I push, otherwise I store LSB address to EE address, EE ADR. That means the LSB of EEPROM address. For that, I am storing it. But while storing it, I write shift by one time. Why we are doing it? Because in my file, right, we have totally 3 program data. Each program data is 2 byte in size. That's why we get 6 as that is data size, right? No, the 6 bytes is equal to 3 programming word. That means half of the size will be, if they say 6, you will have only 3 addresses are enough to store 2 bytes of program data, right? Now all 6 bytes of program data can be stored in 3 address itself, right? Now that's why we are right shifting it by one time. That means that is equal to divided by 2. When you right shift something which is equal to divided by 2, so we add right shift the 0 by one time, again we will get 0 only, right? Now so we store that 0 and MSB is stored, MSB of the address stored is as such. And then we are having I think we cleared the count to 0 here. Previously, we had count and amount, both are equivalent to, both are equivalent to 6. But when we decided to write, we clear the count to 0. If the count is 0 and it is less than amount, that means less than 6, we come here, we take the first byte from the buffer, data buffer, and assign it to the data, EE data, LSB, and then that is the next byte from the buffer is taken and is assigned to EE data H, because 2 bytes of data is flashed in a single address. That means 14-bit address. Right. After doing it, we are we enable we select EEPGD button, which is not PGD flag. We set that flag because we are going to write it to program memory, not to data memory. If it is data, we have to set this value to 0. So we enable write, and then we also disable global interrupts, because if some interrupts happen, program control will transfer there so that it may affect our writing operation. That's why we disable globally, interrupts globally. So I have taken all these inputs, all these steps from the assembly version, from the data sheet of this microcontroller. So I didn't write it by own. I just converted that assembly program into C program. That's all. So after that, this is the writing sequence. So you have to load 55 to the contour register, and then EA to that one. And we have to set the write flag. After that, we have to wait for 2 no operations. Then we have to clear the status. Then we have to disable write enable. That we disable it, and then we enable the global interrupts. After that, I move to the next address. Every time when I move to the next address, I have to move 2 data bytes, because I already flashed 2 bytes, no? So I have to, next I have to, 1 and 2 are flashed. Byte 1 and 2 are flashed. Now I have to pick the 3 and 4, right? That's why I increment the count by 2 right now. While flashing that into the memory, we have to do that in 4 bytes batch. We have to flash 4 bytes one time. In a one batch, because the flash memory, no, it will do a batch flashing. So we should flash 4 bytes at one time, right? For that, we are checking whether we have reached 4 bytes by adding LSB address, program address with 3. When you do that, what you are extracting last 2 bytes. So when you extract the last 2 bytes, you are checking whether they are not equivalent to whether they are equivalent to 0. If it is greater than 0, you have not achieved 4 bytes. How? See, I have first byte. In that time, E address will be 1. Address will be 0, because we incremented that address here. No, so 1. When I extract 2 bytes from and 1 with 3, I will get 1 only, right now. So 1 is greater than 0. So I have not reached the 4th byte yet. So I will go for the second iteration. At the end of second iteration, the EE address will be 2. 2 is 1 0. 1 0 and 3 is equivalent again 1 0. Right. So 1 0 is greater than 0. So again, we have not reached the 4th byte. Then we go for the next time. Then we get 3. 3 and mod 3 0 1 2. Sorry, 0. Yeah, when it become 3, when you add that with 0, again you will add that with 3, you will get 3, which is greater than 0. Again, we will go for it. So when we reach 4th byte, right, that is 1 0 0, and so we will get 0 here. The result will be 0. When it is 0, we come out from this batch writing and we go for the next batch. Next 2 bytes will be taken, and they will next 4 bytes will be taken, then that will be flashed. Like that we will do. Once we completed our writing, we say write OK. So this is the program. If you, this is what the program required. This is what the bootloader is. How this much simple, but this it does not cover all the scenarios, but it is straightforward, simple. It is working, but it need a lot of improvements that I am going to do in day by day. The today I am going to say that is why we have this session today. I want to say that we achieved the bootloader implementation. We are able to flash the software from the PC. We can transfer that to via RS2 and the bootloader is taking it and flashing it, and I am able to execute the program. To prove that I created today video. So now most of you, some of you may be understanding it, some of you may not. Those who have previous programming experience with that is microchip knew that right now. So our plan is we are going to create a demo ECUs for our training. So when we establish the training sessions in this one, we will explain that in detail. Right. So now I have given you a high level overview. Those who know programming really understand what I am doing here and how I achieve the bootloader right now. So the things are ready. Let me do that. When we create an executable, always the executable will be created from the starting address of the microcontroller. So maybe I start from 0. But our aim is to offset the bootloader to the very bottom of program memory. No. For that, the trick used here is, I think I got the idea for this trick is from their sample code only. Here is an example that they are doing. What they are doing. See, they are computing bootloader top, that is loader top. I think this is the loader size. Then what they are doing, they are actually it is 0. Loader top equal to PROG high, right now. Pro high. The pro high is computed here. Right. 1FF. So loader start equivalent to loader top. That means 1FF. That is last address of program memory of PIC controller minus loader size. That means 180 words from the bottom plus 1. So that is the loader start. They are using that techniques. So what I did, I just computed the offset, that is loader start, and then I just encoded that in a linker of this MPLAB ID. So what I did, I just went to properties. Right here, we have linker, no? Here I put that address. That means I offset. I push my code from the 0 address, 00 address to 1CFF. From there, my bootloader will be there. Right. The moment I flash this one, my bootloader by default activated, and it is ready for programming. So when I transfer the bytes from the PC, it will receive that and will flag that from the beginning of the program memory so that my bootloader and my user code will not overlap each other. There won't be an overwritten, there won't be any overwritten, right? So after making this offset, this is very important. You have to do, otherwise you will when you don't do offset of your bootloader, it will overlap with your code so that nothing, you will not get any output out of it. Okay, now after doing it, to flash, so to flash it, first we have to build it. So let me build. So building is over. The X file is created. Let us see the this X file. So this is the X file. Right. So see here, it starts from 39FE. So it is their interpretation. So, but when I flash and see the address in the memory of microcontroller, they start from the address that I created the offset. From there only, it is flashed. So this is the hex file for bootloader. We have to flash this. How to flash it? We have to use a traditional method only. So what we use a flasher, no? We use a flasher to flash it. So let me flash the bootloader now. So for that, my microcontroller, I connected my microcontroller to flasher now. So after that, I am just going to erase my controller because previously I tested this bootloader. So I just first I just do a simple read. After doing it, I erase it. So my complete microcontroller is empty now. Now I just import X, which is nothing but bootloader program. Right, then I just write that program. Okay, the flashing of bootloader is successful. Now I connect my microcontroller to motherboard. Now my microcontroller is with the motherboard. I turn on my motherboard. Now I have an application, no, just Sasa. So let me, this is just Sasa. So let me tell you like how to bring Jesasa fast. So I just stop. So to bring Jesasa, just run this file. This will bring Jesasa. All right, this is this is a very simple version. Here, go here and select serial programmer. So now it is open. Serial port is open and the things are ready. Now we can send bytes to microcontroller for flashing. Already the bootloader is flashed and the microcontroller is ready to receive the data and flash. So we need a program now. I have a simple program to blink the LEDs of motherboard. Right. So let me bring that program. We will simply copy paste. Right. This is the program. So I just copy the first record from the file hex file. This is a program for LED toggling, but I am not flashing it using flasher. I use my bootloader to flash it. So just I paste my record, paste that record to my JSON software. I have to include a E3 command, which is used for flashing. Right now, as per documentation. Right. So E3 is the command for flashing. Right. Sorry, E3 is command to write. Right. After doing it, just I send, I get the response. Maybe you may not understand what it is doing. Actually, this is the checksum from the PC. This is checksum computed by microcontroller. Both are same, so that our record is flashed perfectly. So going forward, just I copy the second record and paste the second record. And I again send that to microcontroller. I again get checksum match. Then third record. Fourth record. So then final record. Okay, that's all. The things are 9C, 9C. Yeah. So the things are fine, everything done. But why I am not doing these two? The very the next line is a configuration word. We already have a configuration word is flashed in the bootloader, so we need not do that when we do it when we do user program. So that configuration may, if we do flash the configuration, and that may disturb the bootloader activity. That's why we are not doing it. And then the very last line is just to indicator end of file. So we can ignore that line. So that's all. Our flashing is over. If I produce a reset, microcontroller will start running from zero address, so that my program will work. That is the expectation. Right. Let me do a reset in my controller now, in motherboard now. When I make a reset, automatically my program is executing. I am seeing LED blinking. That means my code is flashed via serial communication. I have achieved the bootloader, that working bootloader, but maybe I have to do a lot of improvement to that one. But the core thing for this automotive ECU development is done. Right. Okay, team. That's all for today. Okay, team. That's all for today. My bootloader is working. Let us explore the next step in our ECU development in upcoming session. Thank you. Thank you for your patience.